It
is not saying, sir.
No,
This
no.
call is now being recorded. This call is now taking notes.
Just a minute, sir. Sir, now is it visible?
No, sir. No, it's visible, but it is in not in presentation mode.
Okay, sir.
Yes, sir. Now it is presentation mode.
Okay, sir. Thank you, sir.
Thank you.
Yeah, sorry for the disturbing. Yeah, we'll move for the topic today. So, as the coordinator given the topic like subcritical, supercritical CO2 based solar thermal system. So here, before moving towards to this topic, so we'll discuss about what will be my presentation content. So it will be like introduction about the energy and what are our objectives to fulfill the details or the requirement of the world and how we can adopt the methodology for fulfilling all these objectives, and we'll move towards to the whatever we did some research, and apart from us other researchers, they are working on this solar thermal system mainly based on the CO2 based system, and then we will have the question answering session. Yeah. So now, as we know, all of we are aware about the energy consumption. Especially today, we are seeing the increasing the population. So everyone wants the comfort level everywhere. So we are not compromising regarding the comfort. So here we require the energy. Okay, so one has to be fulfill the demand of all these requirement of the world. So it may be you and me, or it may be even if it starts from the farmers to the industry. Okay, so there, like in case of the food, the farmers are responsible. In case of the technology, we the technocrat are responsible for fulfilling the demand of the whatever the world. So again, the energy is one of the main thing. So everywhere we require energy. As we already know about energy, neither be created nor be destroyed, but it can be converted from one form to the another form. So this generation of the energy, we are just converting. We say it is a generation, but we are converting, or we are from hydrocarbons to the maybe the electricity or some kind of energy we are converting mainly from the primary source to the secondary source. So there are different types of conversion of the energy. So mainly what happens today's era, so to meet this demand, we have to make the conversion or generation of the energy, which is very important because we should not contaminate the environment. So everywhere we are looking towards we are seeing the different meets, G20 summit, different summits we are seeing. Here all the nations, they are coming together and they are discussing to increase the usage of the renewable energy and minimize the usage of the non-renewable energy sources so that we can maintain our ecological system. Ecological system, which is very important in this world. Even see, if you observe the whole world, if the human being is not present in the world, so what would have happened in this world? So some people, they will think that So there will be nothing apart from the human being, but it is not. You have the different systems like animals or the even plants, everything. So the human is a one person who is like using all these resources for his own purpose. It may be comfort, it may be a safety purpose or a different requirement, but he is contaminating the environment because of using all these resources. So that's why what happens, even without human also, this world would have been very nice. But we are into this world and we are making all the contamination. So that's why all these summits, they are talking about the ecological balancing or the imbalancing. Means we have to balance the ecological system. So there what happens? Today we all are again witnessing the use of the automobile as we are witnessing today in 2025. So automobile sector is increasing, semiconductor sector is increasing, where at the same time, while utilizing all these things, so we are emitting the CO2. So that's why pollution, which is becoming one of the major issues everywhere. So even yesterday only we have read in the newspaper that Delhi, it is having the worst air quality, so which is affecting towards to the human being, those who are staying in the near around Delhi. Okay, so that should not happen. So that's why CO2 is mainly one of the currently responsible of all the 60% of the greenhouse effect. As earlier speakers already discussed about this greenhouses. Okay, where because of this greenhouse, the whatever the CO2 which is not going towards to the outside of the atmosphere, which is increasing. That is the major thing which one should have in their mind, and we should work on that. So next we are coming towards to the to overcome all these things about the generation of the energy, about the pollution which is affected by the CO2 or the CO different gases. So there we have to see the alternative resources. Okay, so this FDP is mainly focusing on the alternative things to have the sustainability on the earth, right? So that's why. So we all are know whatever the sun which is naturally available to us. Okay, so this sun energy, sun nothing but the solar energy which we are getting from the sun, which is abundant in the nature. This, if we utilize it properly, so there will be we will meet the demand of the whole world. Even if you use the only one day of the total energy which is coming from the sun, we will meet the demand of the whole world of 1 year. So that much of tremendous energy which is we are getting from the sun, and it is a clean and the sustainable energy. As we can say that approximately 1.8 into 10 raised to 11 megawatt of this radiation which we are getting or the intercepting from sun to the earth, it is very important. So there again, as we already discussing about this all the non-renewable energy sources, so we should move towards to the renewable energy sources. So if you consider the solar, so there will be the different types of applications, low temperature applications, even the high temperature applications. Low temperature applications like heating, we are heating like a normal, we are drying the clothes or the any food, or cooling purpose also. We are using the cooling refrigerations with the solar. But in a higher temperature solar thermal systems, like we are producing the energy, electricity. So as earlier, which already discussed in earlier sessions, like concentric type of solar collectors, parabolic type of collectors, where we are utilizing this low temperature as well as the high temperature applications. So there, if we move forward, as we know the non-renewable and renewable energy sources. Today, we are witnessing the price of the petrol or the diesel. So when we were in a childhood, it was around, the petrol price was around 30 rupees per liter. So today we are witnessing 104 rupees per liter, even though we are not compromising in the buying the cars or the automobiles. So which is one thing. Because of this, the prices are going high and high, and where we are not meeting the demand of the customers or the world. Even the coal is having the whatever the India is having the coal reserve, we are not having that pure form. Okay. Even sometimes we are importing the coal from the outside. So here the availability is very less. Even if you consider the nuclear, we know the 1 kg of this nuclear energy. But if you use the uranium of 1 kg, it will give the tremendous energy or the electricity towards to utilize. But the drawback of, we already know about the Mercury. Okay, how she did all the research on that. Okay, even the natural gases today we have the CNGs, LPGs. Okay, but until unless like these things are the where the non comes under the non-renewable energy sources. These are getting depleted. So we are witnessing or we are hearing that up to 2050, so all these whatever the non-renewable energy sources will be vanishing, or these are getting depleted in a very exponential manner. So that's why one should have the renewable energy or the alternative energy. So there, as one is the wind energy. Through the windmill, we can generate the electricity or the hydropower. So today, even the hydropower, there is a 50-50, like renewable and the non-renewable energy sources. Okay, mainly means sometimes we consider it as a renewable energy sources where the water is available. Okay, and the solar energy, then the geothermal and the biomass. So out of all these 5 renewable energy sources, okay, even we have the tidal different, the percentage of utilization will be very less comparing to all these energy sources. Okay, so out of this, solar is one of the best alternative for the this non-renewable energy sources. If you see the energy consumptions of worldwide from 2000 to the 2050, if you see the this blue color indicates the oil utilization, natural gas is the black, coal, then the nuclear energy, hydroelectricity, and the renewable energy. Currently, we are in 2025, where the maximum utilization of the coal is going on. Where the natural gas, it is somewhere like it is a constant throughout from last 5 years. Okay, but the hydroelectricity is also the constant. The yellow color which indicates the renewable energy. Okay, so out of this 617 exajoules, we are utilizing a very minimum amount of this renewable energy. Okay, so if you forecast for the further up to 2050, so as through the researchers or the different resources, so we will be having the more utilization of the renewable energy sources, and maybe because of the depletion of all these non-renewable energy sources, if you see the this coal which is minimizing here. So once what it indicates, like all the researchers or the technocrats, they are thinking about utilization of the more renewable energy sources and minimization of the this coal or the non-renewable energy sources. So that's why even if you see the country-wise, the consumption of the energy up to 2024, okay, So here from the bottom, it starts from the Indonesia, Germany, Saudi Arabia, Iran. Okay. So comparing, the China is in top. Even though they have the more population, they stood first in the world for the population. Second is the India. But comparing all these, okay, all these nations, the India is standing at the third position. Means even the utilization or the primary energy consumptions like a coal, whatever the primary things which we are using, which is in a third position, where China is almost four times, more than four times than the India in the primary energy consumption. Means what I try to say here, even though comparatively to the United States and the China, we are utilizing less because we have the more population, but at the same time, like Russia, Germany, okay, there are different countries where the population is very less, but the utilization of the energy is more. So that's why even whatever all the developed country you see, there the utilization of this energy is increasing drastically. So one should have the alternative for this. If you again see the consumption of electricity per capita worldwide, means one person how much he can consume the electricity per year. If you see uh, this graph, so India is somewhere in the right side. So this is the India where 1418 kilowatt of hours per capita, means every year the person who staying in the India, he or she is consuming 1418 kilowatt per hour. Comparatively, if you see the left side, the island, Norway, Qatar, Kuwait, so there the consumption is more. If you see the 51,920 comparatively with the 1,400, it is almost 40 times more, 40 to 50 times more, which is more, right? So we are little bit lucky that in India we are using the energy consumption which is very less comparatively with the other nations, but because of the population and the demand, the availability of all these energy sources are very short. So one should think about the alternative resources. So alternative resources, which we already discussed about the renewable energy sources, where solar is standing in a first position, where we can see the solar energy, how we can utilize. One is this solar PV, where BIPV means building integrated PV cells, where nowadays everywhere we are installing the PV panels to get the electricity, and even the PV plants, right? And regarding the solar thermal, without means this solar PV is for the electricity purpose, and second one, this the right side, which is the non-electric part. There we have the solar water heater, solar air heater, solar cooker, and the solar cooling systems. Okay, so these things are the low temperature applications. Okay, at the same time, in the electricity generation, we are using the dish type collector, parabolic type collector, or the power tower, or the like a concentrate type of collectors we are using. So this is the one part where we can use the solar energy for the electricity. Okay, then application for the heating and day lighting, so which we all are utilizing. Every human being or every even the plant also, it is using the solar energy, right? The photosynthesis happening because of the solar energy in the plant. Even the animals or the human being we require. So today, we human being are witnessing that every almost in a city level, like a urban, where the people are having the like a vitamin D deficiency. So from where it is this vitamin D coming? Which is from the solar energy. That is the sunlight, right? So even we are getting the injections of this vitamin D, but which is again, I'm not going deeper into that, but which is again the drawback to the human being. So that's why the natural things we are getting, that is the heating purpose, like normally from the solar system. So there are as like 7 different applications of the solar energy. That is the generation of the solar power, water heating, even the dry agriculture products, solar heating, solar lighting, solar pump irrigation, and the solar distillation. So now, out of this, we are diving towards to the this solar water heater system. This is the basic one which everyone require, right? So, we are getting the solar energy for the like a vitamin D. At the same time, everywhere in the India or throughout the world, okay, the heating of the water mainly, basically, we are using the solar energy. So there, the concept, if you think about the solar water heater, the world first solar collector, which was invented in 1767, okay, by the Sweden researcher, that is Horace Susure, in 1767. And later, there was the advancement in the solar water heater, because what happened in 19th century, so because of this World War One, Two, so there was the crisis of the energy. So because of this, what happened? The spiking of the oil prices, right? So which made to more research or the dive into the solar energy development even further also. So that's why, if you all are aware, so from last 15 years, we are having the more focus on the solar energy, mainly installation of the PV cells and as well as the installation of the solar water heater. So now I'm coming towards that the difference between the PV cell and the solar water heating system. Where for the electricity, we are using the solar PV cells now, okay, but the efficiency of this PV cell, which is almost maximum 20%. If you use the direct solar heating system, so which is almost 60 to 70%. If you compare these two, so this direct utilization of the solar system, which will stand far more than the this PV cells. So that's why we are looking towards to use this solar energy to generate the electricity directly instead of the PV cell. So that's why maybe the tower or the concentric type or the parabolic type of collector where we use for the this energy generation. Okay. So if you see the here in the picture, we have the 2 different types of solar water heater. The right one is the flat plate collector, and the left one is the evacuated tube collector. Okay, so people they're saying that like a flat plate collector is having the less efficiency than the ETC, because it is having the ETC is having the vacuum, that is the evacuated means the vacuum, where as we know the solar radiation passes through the vacuum, so no media is required. So the efficiency of this ETC is more. But so if we see the which I have written below, that the total renewable energy capacity, okay, in the country has reached almost 220 gigawatt as of last March 2025. In October, it was having around 2,203 gigawatt. Okay. So regarding this ETC and the flat plate collector, so why people are using the ETC? Why not the flat plate collector? And why I'm more focusing on the flat plate collector? So that we can see here. If you see the comparison of this ETC and flat plate, as we know, the quick heat generation happens in the ETC because of the vacuum. But in a flat plate collector, what happens? It will be like a box where the solar energy has to be absorbed by the absorber, okay, which will take a more time. So that's why the efficiency of the ETC is more than the flat plate collector. Okay, so even the convection and the convecting losses are low here, but in the flat plate collector, because of the box, we have to insulate from the all sides apart from the top layer, right? So there the losses will be more. As we know, the temperature of the surrounding, if it is increases, okay, then the absorber temperature also increases, and because of this, the losses will be more. So that we will discuss it later. Okay. So if you compare the ETC, the emissivity is also less, right? Then the temperature range of the ETC will be around 60 degree to 120 degree Celsius, but in the flat plate, 60 to 80 degree. Like we have the advantage. If you compare with the flat plate and the ETC, we have all these advantage in the ETC. But why I am focusing on the flat plate collector? If you see this graph from 2007 to the 2023 in India, okay, normally the red color indicates the evacuated tube collector installation. For the solar water heater, liter, we are measuring the installation in terms of the liter per day LPD or square meters, right? So here, if you see, the installation of the ETC are more, almost in 2023, it is around 16 lakhs, 16 to 17 lakhs. But the flat plate installations, which is diminishing from 2017. Okay, so if you see the 2012, 13, it was more, and in 17 also more. After that, it is diminishing. Okay, so it is minimizing. So one should think about this flat plate collector, because even if you see the price of this ETC and the flat plate collector, okay, the flat plate collector, which is almost maximum 10,000 rupees per 150 liter capacity, or even less than that. But the ETC cost will be more than that. It is almost double. Okay. So the applications of this flat plate collector, here we are seeing the different like yellow color, right? So where these applications are, where these are installed, mainly if you consider the these hospitals or guest houses, hostels, where the maximum number of human beings are staying or the requirement of the water is more, there the cost also matters. Okay, so these are flat plate collectors are installing such type of application or such type of locations. Okay, so that's why we were focusing instead of ETC earlier. We were focusing towards to the this flat plate collector, so that we can improvise the efficiency of the flat plate collector. The all the human being or the every individual can have the flat plate collector in their home or in their places. Okay. So before moving to the improvement in the flat plate collector, just I will tell about the different circulations of the this loop or the cycles. Okay. Mainly, if you see the solar water heater, right? So we are not using any pump or the heater in the solar water heater. But today, even we have that provision that like winter, it started, right? If you go to the north India, where the temperature will be today in Pune region also, we are witnessing around 10 degrees Celsius. But if you go to the north India, it will be less than 3, 4. Okay, so there today if you go and buy the solar water heater system, there the suppliers have the provision that the heater will be installed in that, as well as there will be the pump. If you see the right top of this figure, here it will be seen the pump is also there, and as well as the heater to heat the water. But we all are talking about the minimization of the energy consumption, or the meet the demand of the customer or the whole world. But we are again utilizing this energy, right? Solar energy, if you use directly, I will agree that we are minimizing the other resources. But if you use the pump and this heater, again we are adding the more consumption of the energy. So that's why here, if the moving parts comes like a pump, compressor, or the heater, the energy required, which will add the more energy consumption, which should not be happen, right? So for that, whatever the natural source of this flat plate collector, like the left side you can see, okay, which is a natural where we don't have the pumps or the any heater. Okay, normally what happens from the flat plate collector, the water which will get heated through the solar radiation, and it will go because of the buoyancy force, and the heated water we can utilize it for the our domestic or the industrial purpose. Then again the from the overhead tank, the water will come to the at the bottom of this flat plate collector, and this cycle will be repeated, right? So if you think this, we have seen like what happens. Normally, the 80% of the global solar market, this solar water heating system we are using, okay, though the direct solar water heater system. So this is nothing but the direct solar water heating system, because the water is coming from the overhead tank and it is getting heated, and we are directly using for the domestic purpose, right? So if you don't have the water at the overhead tank, there is no supply of the water, right? Here what happens, if you see this direct type of solar water heating system with a flat plate collector, which is having the minimum operating cost and the maintenance. But what happens, these things are more suitable in the summer. If you see the solar water heaters in a summer, we will get the more hot water. But as the performance decreases during the winter season, because what happens at, as I told, the North India, where sub-zero temperature we can witness the sub-zero temperature, where the utilization of such a direct solar water system finds very difficulty due to chance of water freezing. Mainly what happens in a night, because of the low temperature, because the panel's top layer will be, if you just a minute, if you see this solar water heater, the top layer which is directly exposed to the atmosphere, where what happens, the inside the collector, whatever the water is circulating here, okay, so in this tube it will get freeze in the night, and even in the morning, even if you get the like a sun intensity of sun rays, okay, so it will take a more time to get heat. The whatever the water which get freezes inside, it will take more energy to get convert into from ice to the water. Then that water has to be get heated towards to the required temperature. So here what happens, the low temperature, the energy required to drive this flow is much higher due to the high viscosity of this water, because it converted into the ice. So the effectiveness of the solar collector, which drops drastically in the morning, and it will take a more time to get the warm water. Okay, so that's why sometime what happens, because of the freezing, there may be chances of bursting this system, so which should not happen. So that's why what we were discussing. So there, instead of that, whatever the direct type of solar water, we can see the indirect type of solar water. If you see the bottom right side, okay. So here the flat plate collector, and which is having the uh, this heat exchanger here, pipes inside the tube, right? So what happens? Whatever, instead of water, you can use a different types of fluids which will get heat and which will give the energy inside the storage tank. And the water which is inside the storage tank, it will absorb the energy, it will get heat, and again the cooled liquid in this loop, which will coming back again to the this collector. So that is the natural circulation loop, which is a closed loop, which we call it as a natural circulation loop. So mainly it is not only in the heating, even if you see the nuclear power plant, where the reactors, okay, there we are using the this NCL, that is a natural circulation loop, okay. So one should utilize this natural circulation loop so that we can minimize the energy consumptions. Okay. So in a natural circulation loop, what happens? The whatever the fluid inside, it may be different fluids. Okay, which is absorbing the heat from the solar radiation in a collector, and which is exchanging the heat in the this storage tank. So circulation of this loop is maintained due to the buoyancy effect, right? So that's why we call it as a natural circulation loop. So whatever the fluid which heats because of the density difference and the buoyancy effect, okay. So almost this solar water heater, which is inclined, normally it is up to 45-degree inclination. So because of this inclination, the heated fluid will go at a upper level. So this happens because of the buoyancy effect. Okay. So if you come towards to this natural circulation loop, there are different types of loops are there. Okay. So depend on the applications. If you see these figures, okay. So one is the point heat source and the point heat sink, toroidal loop or the rectangular loop. So there are different types of applications are there. Okay, if you consider the shape of the loop, so this shape, whatever we are seeing in the toroidal loop, even the tube and tube heat exchanger, like that. Okay, and if you consider the state of working fluids, it may be a single phase, two phase, or the supercritical fluids. Like you can have the single fluid or the multiple fluids, but their phases will be the different, or even the number of heated or the cooled channels, single channel, multi-channel, or it may be a body force field which having the gravity or the centrifugal forces. So there are different classification of the NCL. So here we are moving towards to this state of working. Here single phase, two phase, and the supercritical fluid. So out of this, we were in the research of this single phase and the supercritical fluid. Okay. So what is the advantage of this NCL or the natural circulation loop? What happens? We are not using any blower or the compressor. Because of this, what happens? Which is having the low cost, and it will become a simpler one. And as I told earlier, no pumps are there. Because of this, the improved flow circulation will happen, and flow is having the different structures and the safety concern. So because we are working with the atmospheric pressure, okay, the disadvantage of this NCL, which is require the driving head, as we discussed the earlier slide. In the morning, it is very difficult to get the hot water from the this solar water heater. Means the driving force requirement is more. That is the one thing. Then less mass flux. The amount of flow of the fluid is less, it will be having the instability also. Sometimes what happens in a pipe, inclined pipe, when the fluid gets heats, so the heated fluid again it will be in contact with the low temperature fluid, so it will mix up there itself. So that's why instability comes into picture, and the low pressure, low flow regime also happens. So that's why one should have the proper utilization of this NCL, which is depend on the selection of the working fluids. So to overcome all these advantages, we can have the this is the disadvantage of the this NCL. We should have the proper selection of the these working fluids. Okay, so there the low viscosity, whatever the fluids which we use, that should be low viscous, and it should have the low freezing point, right? Even see example like we are putting the nitrogen in the tire of the automobiles, okay, where because of what the expansion or the heat carrying capacity will be more, it will means it will not get heated as much as the normal air which we put, even though in air nitrogen percentage will be more, but a pure nitrogen we are putting into the vehicles. Okay, so like these all the things comes into picture, like in the solar water heater or the natural circulation loop, one should think about all these points. That is the low viscosity, low freezing point, high volumetric expansion coefficient. Because once it get heats, it should get expand. Means that should be high. Environment friendliness, high specific heat, high thermal conductivity. Then it should be a non-corrosive, a chemically stable, and the non-toxic. Also, it should available abundantly everywhere in the nature of the world, and cost should be minimized. If you see the availability is more, then definitely the cost of that particular thing will be less. So that one should think about while selecting the fluids. Okay. So this natural circulation loop, as we discussed earlier. So what are the different applications of these things? One is the solar thermal system. Example is the solar water heater or geothermal power plant. You can see here geothermal power plant where the heat source, from the heat source we are getting the heat, okay, which will get condensed, and that fluid will go to the turbine. Okay, so it will give the heat to the this turbine connecting with the generator, and we are generating the electricity, right? After that, whatever the fluid from the this heat source, it is again coming back to the cooling tower, and it will get cool. At the same time, we can utilize that heat in the cooling tower, and the cooled one again we are letting into the heat source. So this is the geothermal energy. We are not going in detail. So this is the one where we are using the natural circulation loop means whatever the heat energy which is coming from this heat source to the up to the turbine. Okay, so there the natural circulation loop plays a vital role. Okay, then also in the thermal power plant like a boiler furnace. Okay, even today in a boiler or the furnaces they are using this NCLs. Even if you go to the sugar factory, there the superheaters are there. There we are using the natural circulation loop, and cooling of the transformers. There we are using the NCL, electronic cooling, as well as heating, ventilation, and air conditioning system, and the nuclear reactor. If you see the nuclear reactor here the this left side, the control rods, which is having the pumps, right? So this is a normal one where if you are not using the natural circulation loop, if you see even from the cooling tower here, we are using the pump, right? And here also we are using the pump so that we can circulate the thing. But if you use the natural circulation loop, we can minimize that one. If you see the right side, where this pre-cooler, okay, from pre-cooler to the compressor, and even the Here SCO2 flow means supercritical CO2, which is flowing towards to the reactor. There is no any pump because so the CO2 is having the more energy. So that we are going to discuss in the later part. Means these are the different applications where we can use this natural circulation loop. And while using the natural circulation loop, so there will be the different fluids available. Like example, even we are using this refrigerants. Okay, so if you see every maybe 2 to 3 years or the 5 years, we are having the different names of the refrigerants, right? So suitability of all these refrigerant or the secondary fluid, which is very important. If you consider for the natural circulation loop, we are using the CO2. Mainly, we are focusing on the CO2. If you see this table, we have the different types of fluids where it starts from the calcium chloride to the last one, the carbon dioxide, right? So here, if you see the density, if you compare with almost carbon dioxide density is less, heat carrying capacity CP is almost high. If it is the water, water is little high, okay, but the density of the water is more, but the conductivity comparatively it is less through to water, okay, but the viscosity, okay, which is also less, and the this beta thermal expansion coefficient, which is very high comparing to all these fluids. If you see from the table, calcium chloride, which is having the 0.000114, but the carbon dioxide, which is having the 007398, which is the thermal expansion coefficient, which is very high comparatively with the other fluid, and the freezing temperature. Freezing temperature of the CO2. This is the -56 is the triple point actually. Okay, means if it goes to the -56, then it will go towards to the solid part. Okay, so here that's why the suitability of the CO2 as a working fluid. Why we considered CO2 as a working fluid for our applications. Okay, if you see this schematic of the CO2 phase diagram, okay, the blue line indicates from the phases. So this is the solid phase, liquid phase. So this point A is the triple point where the triple point is at a -57 degree. Okay, the supercritical, which is having the 31 degrees Celsius. My question is, so suppose if you take a water, okay, so if you want to convert this water into the supercritical fluid, so what will be the temperature and pressure? Maybe in a supercritical temperature above 100 degree, it will convert into vapor. But what about the pressure? Pressure will be very high, around 400 bar. So maintaining the 400 bar is very difficult. So that's why instead of water, we are going for the alternative fluids. So out of that, CO2 is one of the best fluid. Why it is so? It is having the high latent heat of vaporization. As we see here, the low freezing point is -78 degrees Celsius, and the high volumetric expansion coefficient. And the beauty of CO2, using the CO2 is the critical points. The critical temperature of the CO2 is 31.1 degrees Celsius with the critical pressure of 73.7 bar. Right. Even today, if you see the atmospheric temperature in the afternoon, mid-noon, it will be around 35 to 37 or maybe 40. Means in a normal temperature also, the CO2 will be in a critical position. Any fluid which is working near to the critical point, which will give the better efficiency. This is the one of the biggest advantage of from this CO2. And at the same time, this at a lower critical temperature, we will get the more pressure. 73.7 bar. If you see, to get the 73.7 bar of pressure in the water, we have to heat more. right? So that water should have the more than 100 degree, means it is in a vapor phase, it should be. But in the CO2, we will get this high pressure within the low temperature. That is the critical point, which is really a beauty of this CO2. At the same time, which is having the low viscosity and high specific heat, also the high thermal conductivity, and which is having the ODP 0 and the GWP, which is 1. So if you see, so this is we analyzed with the help of the RefRob. RefRob is a software where we can have the all these different properties, physical properties of the any fluid. Okay, if you compare the CO2 liquid at a 60 bar, if you see before that, here solid, liquid, and the supercritical. See, supercritical will come after 31 degrees Celsius, and the liquid phase, which is minus 57 degree to up to the 31 degrees Celsius, right? So that's why while doing the comparison, 283 Kelvin means almost 10 degree, okay, which is less than the critical temperature. So at the 10 degrees Celsius, the CO2 is having the 60 bar, and the water normally in a 1 atmospheric pressure, right, at a 10 degrees Celsius. So if you see the ratios, okay, high thermal expansion coefficient, CO2 by water is more, and even the Prandtl number, Cp, everything, okay. So the mu is also more, okay, in the liquid phase. If you see the supercritical above the 73 bar, that is the 90 bar with a 313 Kelvin, means almost 40 degree, right? At a 40 degree, if you see the CO2 to water, the thermal expansion coefficient increases, right? 1012 to 256, which is very high. Even in the here mu is 18.64, right? Means the difference of the density, okay, is more comparing with the water, right? If you see again the supercritical at a 323 Kelvin, means 50 degrees Celsius, the CO2 to water, which is again little bit decreasing. Okay, so this thing we'll discuss it later, because what happens even in a solar water heater, as the outside temperature increases, okay, surrounding temperature increases, the efficiency of the collector or the things also get decreases. That we'll discuss it. Okay, so even we got the result in terms of the different pressure. We compared this water-based system with the CO2-based system. Water is normally we are using at a 1 atmospheric pressure, but CO2 at a different pressure, 50, 60, 70 bar. At a, see, this is a T average is 283, which is in a liquid phase, and T average is a 323 K right side, which is in the supercritical. Okay, so if you see these two figures, the heat transfer rate, okay, so bottom here, this line indicates the water line, okay, with a star in water line, and with the as increase of the pressure with the CO2. So the blue line indicates at the 70 bar, then the red 60 bar, and black is a 50 bar. Means if you compare with the CO2 with the water, increasing the pressure, the CO2 is far better in the liquid. Okay, at the even at the lower pressure also, it is giving the more good result than the water. At the same time, for the supercritical, if you see here, water is 1 atmospheric, but 80 bar, which is just below this water line. Okay, so this we will discuss it later, because the pseudo-critical temperature, pseudo-critical point comes into picture here. Even At the 90 bar, which is having the more heat transfer, that is the more than, if you see the temperature difference, delta K, okay, means inlet and outlet temperature. So here it is having up to the 400 watt, right? But in a 100 bar, it is having more than 1000 watt. Means what these figure indicates, that is the heat transfer rate with the change in the, means with the delta T, means the whatever the fluid which is coming and getting heated and which is going out of that, right? That is the delta K, different delta K with the different delta K. Sir Kate sir, can you mute the video? Okay. So here, what happens? The CO2 supercritical based thing or the system which will having the more advantage. Okay. So with this, what we observed, like a major of the studies have been which conducted on the direct type of water-based solar thermal systems. As currently we are seeing all the rooftops, whatever the solar water heater. But there is a scant of research uh, or the indirect type of CO2 based solar thermal systems. Means whatever we discuss right now, instead of the direct water, we can use the different fluids in that loop, and we can utilize with the help of the heat exchanger. So that is not available in the market as well as in the society. Okay, so that's why one should have the proper research with the experimental and the numerical things on this. So here the comes why we are more focusing on the flat plate solar collector. If we do the good research in this area, flat plate solar collector, maybe with the experimental numerical or the energy analysis, definitely it will give the more advantage than the ETC. There we can minimize the utilization or the cost of the system also. Okay, so as this motivation for this supercritical CO2 based, which we already discussed, like a direct type of solar water heater, which is more suitable only in the summer, but in a winter, water will get freezes. So that's why the driving force which require will be more, and there sometime it will the system will get burst. Okay, so that's why. So we thought to work with the analysis, CFD analysis, as well as the numerical analysis and the experimental. Okay, so so this is the system where we converted the normal. So this is not a converted one. We fabricated ourselves with the means incompatibility with the CO2 based system. Here normally we see whatever the tubes we are using, these are the copper tubes inside the this collector, but copper which is not suitable for the higher pressure, because as we know the CO2 which is having the beauty, that is at a 31 degrees Celsius, that is the critical temperature, it will reach up to 73 bar. Okay, so this summer we witnessed around up to 50 degrees Celsius, right? So you think on that, even you can get the data from the RefRock. Okay, with the 50 degrees Celsius, what will be the temperature? Sorry, what will be the pressure, which will be very high. So this pressure, which is for the this copper tubes, which is very difficult to handle. So that's why whatever the tubes which we used, everything, the connections, these are SS304 or the 310 stainless steel. Okay, this stainless steel, even though it is having the less conductivity, but which is having the capacity to hold the maximum pressure. Okay, so this collector size was around here it is given. Okay, we had the different header tube diameters, even riser diameter. Okay, we did the TIG weldings, okay, because here it is having the SS, okay. So this is the system parameters which we did, okay. So even in the simulation purpose, so this is the thing, okay. Here whatever the rate where this is nothing but the solar collector on which the solar intensity which is falling on the radiation which is falling on that, and which will get heat, and here it is having the heat exchanger, okay. Here, because if you see this pipe or the line, okay, which is the closed loop, that is the natural circulation loop, closed loop it is not an open loop. But normally what we see the open loop. The hot water comes, we are utilizing, again the cold water come from the okay. So here this is the design. Hello. Hello.
Participants, please mute your speaker mic. Participant, please mute your mic.
Sir, am I audible?
Yes, sir, you are audible.
Yes, sir, it's audible.
Okay, sir. So here, see, this is the schematic diagram of this CO2 based solar thermal system, and here we have the inclination of this collector. Okay, so this is the where we can make the different inclination depend on the different geography, altitude and the latitude of that particular location. Okay, so here we did some assumptions, that is the blue fluid and the external fluid streams are in the single phase. Okay, we were not in a multi-phase, because multi-phase again it is very difficult to analyze the thing. Okay, and the external pipes of the heat exchanger bottom side, solar collector, everything got insulated properly as we considering the flat plate collector. And whatever the water properties are estimated at the inlet temperature itself, and fouling in the loop is neglected. There is no fouling at all. Okay, we did the energy analysis as well as the exergy analysis. In the energy, we can you can see here, that is the normally Q is equal to MCP delta T, the total utilization of the energy, which is nothing but the absorbed energy minus losses, right? So even in a solar water heater, losses will be more. Okay, so this absorbed energy will be whatever the transmittivity we are having. Okay, emissivity, considering this tau and alpha, so that is the absorbivity, and the utilization is nothing but MCP delta T. T out is nothing but the whatever here the fluid which is coming out of this collector, that is the T out, and T in is here. Okay, inlet of the collector. Okay, then the losses which is happens at the if you see here the collector, the top losses. Okay, TP is the plate temperature, TA is the ambient temperature. Okay, so as the ambient temperature is more, again the losses will be more, as even we have seen in the second session. Okay, as the ambient temperature increases, losses from the solar systems will increase. Okay, so here with this even the efficiency we can find out with the help of the whatever the utilization of the energy, then intensity with the area, that is the efficiency. Okay, so here while doing the this exergy and energy analysis, if you see the diagram here, thermal sources where the EXN is the exergy analysis, E in is the energy direction. Okay, so this is from the thermal source to the thermal conversion output, and again it is connected to the sink. Okay, so this is the system where we can have the exergy and the energy analysis. Okay, so in the exergy balance, we can see the exergy in, exergy out, and exergy losses. Okay, and these are the different ED, that is the losses due to the uh, different atmospheric things. If you see here, ED and EL, these are the losses which happens because of the sun to plate. If you see the sun temperature, we are considering 6000 K as a temperature of the sun. So that is the very high comparatively to the top of the this collector. So the losses will be more here. So that we are going to consider. And the second consideration, the flowing fluid and the absorber plate. Because the fluid is flowing below the absorber plate, so there the temperature difference will be there. Okay, as well as the pressure drop due to the friction of this fluid inside the tube. So considering this, we have done the exergy and the energy analysis. So for that, one should have while doing the CFD analysis, grid independent test should be done, because one should get, because it takes a more time, computational time. So that's why if you see the number of nodes where the increases, right, with the grid size, maximum grid size, the nodes are less, minimum grid size, nodes are more. So we did the grid independent test so that we can minimize the computational time and we can get the better result. Okay. So these are the different input parameters for the even the exergy analysis and the energy analysis. We did the validation with the previous researchers also, so that as whatever the things we are doing, whether it is correct or not, somewhere we have to validate it, right? So we did the validation. We almost got the 4% deviations in this, okay, which was really good for further research. Okay, so we are moving towards to the next part, that is the whatever. So this is the our schematic model. Here, if you see, this is the inclination. So this is a solar collector. So this inclination we are changing because it is depend on the latitude, altitude of that particular location. So exactly means in what angle it will give the better result. So first we did the research on this 33-degree inclination. Why it is 33? In a NIT Suratkal, it was the latitude was inclination was the 13 degree. So we took the 10 degree inclination extra, then that is a 33. Normally, if you see 45 degree, we are using, right, for the solar water heater. So here 33, 43, 53, we did the three different analysis. We are coming to the pseudocritical region, where if you see here, so one should understand this graph very in a very good manner. If you see the temperature in terms of Kelvin, okay, and even at a different pressure lines, okay, 60 to 100, okay, if you see this blue line, that is the 80 bar, okay, the CO2 around 80 bar, which act as a like a pseudocritical fluid. Pseudocritical means near to the critical point. Okay, critical point is 31 degrees Celsius. That is the 301. Near to that, it will act a very drastic changes in its physical properties. Okay, at the sudden means in the near to the pseudocritical, it changes its properties, which is not at all considerable, or means we can't rely on that. Okay, so that's why what happens, we should move towards to the above this critical. Okay, so that's why that is the meaning of this graph. And even we did the mass flow rate with the heat flux with a different pressure and a different temperature. If you see this graph, where this mass flow rate of the CO2, which is very high comparatively with the water. Water line is the red line below. Okay, so as you move towards to the critical, where the mass flow rate, we did the simulation as well as experiment with the same setup. Okay, where initially we did all the experiment with the water and later we did with the CO2. So we identified or we got the result where the mass flow rate is very high. Okay, so even we are seeing the velocity contours inside the tube, which is the CFD analysis. Normally, in experimental, it is very difficult to analyze such type of contours. Okay, so here, if you see the velocity contour plot of the water at the collector outlet and the center of the heat exchanger. So collector outlet means where the fluid moves, okay, from the collector after getting the heated. So here what happens, the velocity is more at the center here. Okay, so water velocity is more in the center. Okay, and at the heat exchanger where the velocity is almost minimum here. Okay, even if you compare with the subcritical liquid of the CO2. Okay, this is the first one is for the water one. Second one is for the second. This diagram is for the CO2, where the velocity of the CO2, which is increasing here. See the red line. Okay, it is like a focus of the bulb, right? What happens? The temperature which is increasing inside the fluid or inside the tube, even in the center of the heat exchanger also, it is having the more velocity here. If the velocity is more, it is again depend on the higher thermal expansion coefficient. Okay, so which is having the more advantage than the this water. If you compare with this same water with the CO2 in terms of the temperature. Okay, so this is the graph where the temperature at a 305 is more. So this is the critical, sorry, this is for the supercritical phase where the fluid. So if you see, this is the center of the heat exchanger. After giving the energy to the water outside, the fluid is having the less temperature here. So that's why the velocity counter which shows, okay, velocity is less here because all the energy which is giving to the water. So this is the velocity counter for the CO2 and the water. Also, we have compared with the Reynolds number with the heat flux. Okay, Reynolds number, which is very important to finding the heat capacity or the heat transfer. Okay, we say the uh, laminar or the turbulence. Okay, so here if you see the subcritical liquid, when the CO2 is in a subcritical, so this velocity is sorry, Reynolds number is almost 4,000 to almost 10,000. If you are coming to from subcritical liquid to the subcritical vapor, the Reynolds number moves or goes 8,000 to almost 18,000. Okay, if you see the for the 70 bar pressure of the CO2, so Reynolds number is more. Okay, and for the supercritical, so which is for the 80 bar, see this is near the pseudo-critical, so that's why it is giving the better result. But in a 100 bar, which is having the less. Okay, because what happens as the CO2 moves towards to the 100 bar, the inside temperature of the this fluid or the tube will be more. At the same time, the atmospheric temperature is also more. So because of this difference, okay, or the more atmospheric temperature, what happens here? The losses will be more. So that's why here even the Reynolds number, which is less than the 90 bar and the 80 bar. So comparing with this slide, means if from this slide we can say here, the Reynolds number of the CO2 at a 70 bar to the water, which was almost 159 times more. In a subcritical vapor, which is almost 200 times more. But in a supercritical, which is 262 times more. So comparing the supercritical CO2 based thermal system or the water system, which will give the a better result than the normal direct type of water heating system. So this is the temperature counter for the water. So where you can see here temperature inside the tube or the collector when it is getting heated. Okay, for the water. And for the CO2, this is the thing. Diagram A, which shows if you see the top and bottom, first is for the water case, second is for the CO2 case, where all the water will get heated. But here only the surrounding, means the periphery of this circle, which will get heat and it will carry the heat. Okay, which is the beauty. And at the same time, if you see the right side of these figures, okay, for the supercritical, after giving the heat towards to the water, whatever the fluids come from this heat exchanger, which is having the less temperature. If you see the this temperature, this one from color, okay, from 305 to 322, where the fluid which is coming, CO2 coming from the heat exchanger, which is having the less temperature here, okay, which is again the beauty of this CO2. Okay. So with this, even we did the comparison with the Nusselt number. Okay, so convection to the conduction, where for the water, which was almost constant, okay, but CO2, which was increasing from subcritical to the supercritical, and as well towards to the from liquid to the vapor and the supercritical. Okay, we can see here. Almost in the supercritical phase, we got the better comparison from CO2 to water. Okay, so this is about the Nusselt number. Even we did the energy efficiency also. Energy efficiency normally, energy efficiency is high. Okay, if you see the normal solar water heater system, heating system, whose efficiency will be up to 78%. But if you see the CO2 based system, which is above the 80% almost, okay. If you see the supercritical also, which is above the 80, which is again the beauty of the this supercritical CO2 based thermal system, okay. And the exergy analysis, exergy which is normally which is less than 5 or 6, okay. If you see here, exergy analysis, comparing with the water case, the CO2 is having the better thing. Okay, so here we are considering the top loss also, atmospheric temperature also, and we are considering sun as a source, which temperature is very high. We are considering 6000 K. So that's why this loss will be more. So that's why exergy efficiency will be up to 5%. Okay, but comparing to the water case, we have the better result for the CO2. Even you can see here at the bottom, which is the heat flux, 400, 600, 800, 1000, right? So here what happens, 400 means the intensity which we are getting on the earth. Even the low intensity 600, normally maximum it is 1200 watt per meter square, but due to the attenuation because of this ozone layer, we are getting less than that. So we have considered the different cases from 400 to 1200. Okay, so this was the result which we witnessed. Even the dimensionless exergy analysis also we did. Here you can see the losses. So this is the losses. Okay, as the heat flux increases, the losses increases. Sorry, losses increases. That's why the efficiency is decreasing here. So this is the thing. Also, we have done the with ambient temperature. If you see, this is the one is the energy efficiency, second one is the exergy efficiency. As the ambient temperature increases, the efficiency of the exergy decreases here from 5.5 to 2.5. But at the same time, energy efficiency which is increases, which is with the ambient temperature. If you consider the wind velocity, because again the convection also matters, right? HW matters. Where with a different velocity of the wind, again the exergy and the energy efficiency, these are getting decreases. Okay. So with this, we can say that CO2 based solar water heater yields a very high mass flow rate, and for the same heat flux for the water based and the CO2 based, if you compare CO2 based system in a supercritical, which gave the better Reynolds number as well as the better Nusselt number, and the energy efficiency was high, almost 5.55% more than the water based in case of the subcritical liquid, 12% in case of the supercritical liquid. Okay, so with this one, even we have done the different, like earlier it was only for the 33 degrees Celsius. We have done the simulation for the 43 and the 53 degrees Celsius, and the same what I explained earlier. For the 43 degrees Celsius, we got the better result comparing of the CO2 itself. Okay, CO2 at a 33 degrees Celsius, we did all the parameters. 43 all the parameters and the 53 all the parameters. So here we witnessed for the 43 we got the better result for the subcritical liquid, vapor as well as the supercritical fluid. Okay. Also, this is the experimental setup. We carried out all the testing also. So just 5 minutes, sir. I will finish it.
Yes, sir. No problem.
Okay, so this is the fabrication where we did our own. We have tested. Okay, because this system has to be withstand more than 100 bar. So here you can see up to 125 bar. Even I tried for 200 bar pressure. Okay, so we did the fabrication. Even we did the vacuumization of the system. Then this is the setup. We have the we had the thermostatic bath to maintain the temperature. So here what happens, every time we are not getting the sunlight, right? So because of, as we know, as a researcher, we are more focusing about the results, right? So we should not depend on the whatever the natural calamities. So there, what we did, we made our own this artificial sunlight. Okay, we made the arrangement of this with whatever the sunlight which is having all these infrared rays, ultraviolet rays, everything. Considering this, we considered the different setup and we made it, and we did the experiments. Okay, so here if you see, this is the experiment. Even we like measured the intensity of that whatever the heat which is falling on this collector. Okay, so you see here, you can see for the 400 what was the intensity. Means we are maintaining the 400, 600, 800. Even in the experiment also we did the same thing. And this is the CO2 cylinder where we have the safety walls, everything. Okay, so with this we did even the comparison of the Reynolds number and the tube temperature. Okay, if you see for the 33, 43, 53, we got the better result of the Nusselt number at the 43 degrees Celsius in the experiment also. When we have the error, that is the error correction comparatively numerical and experiment, was almost 2.58%, which is comparatively it is minimum. Okay, so even So with this, we can say subcritical vapor with a 305 K at a 305 Kelvin, okay, which was the better result than the 33 and the 53-degree inclination, okay, and even experimentally, whatever we did, we were having the 11% of the error comparing with the numerical result, because it is very difficult to maintain the all the criteria in the experimental, because CO2, if you see the pseudocritical everything, it is not in our hand, because even it is not a transparent one also. So that's why this is the error which we got almost 11%. And if you see the in case of Nusselt number and all, so we got the 5.8% and the 2.5% error in the means that deviation we got in the experimental. Okay, so overall, if you see the like we got the better thing in the experimental as well as the numerical, so that this is not only restrict to the solar water heater, which the same thing we can utilize it for the electricity generation also in a power plant also. Okay, so this is these are the different like publications we did. So here I'm ending my presentation. If you have any queries, you can ask me.
Yes, sir. Thank you, Dr. Biradar, sir, for the nice informative presentation on the CO2 based solar system. So I think you covered the basic of energy consumption from the worldwide up to the 2050. And again, the position of India in energy consumption worldwide, solar energy applications, then solar-based heat transfer loops, and some geometrical as well as some mathematical modeling for the energy analysis. So it's, I think, nice talk and nice session for our participants who want to work on the CO2-based system. So I request to all the participants, we are having the great time to interact with the Dr. Biradar, sir. So if you have any queries, you can directly unmute yourself and discuss with the Dr. Biradar, sir.
Sir, one question was there. What about the initial cost of CO2 based system?
Yes, sir.
So, see, whatever, like fabricating of the system, normally we are in the process of the patenting also. So it will be around 10 to 12,000 rupees. Okay, 10 to 12,000 rupees. And here the CO2, it is like whatever we are charging in the this refrigerator. Like we have to charge the CO2, and we need not worry about that. It may be maybe 1 or 2 years we can just check it out. And the cost of this filling the CO2 is also very less, almost 9 rupees per kg. Okay, and for whole system it will be having almost 1 kg maximum CO2. Okay, so which is very cheaper than the other like ATC. Okay.
Yes, sir. Any participants? You have any queries or the question? Please unmute yourself and directly interact with the Dr. Biradar, sir.
Sir, good evening, sir. Where
Yeah.
this system is currently used in major, that means where majorly this system is used in large quantity?
Sir, the CO2 based system, normally if you talk about the, are you talking about the solar water heater or the supercritical CO2 based system?
Anywhere, sir. That means what is the vast application of this one? That means I have what is this seminar I have heard first time, that is application of CO2.
Yes, sir. So this is mainly like as we discussed earlier for the even the like a big data handling systems are there, right? Right.
Okay.
So there the cooling is required, electronic cooling. Then the nuclear power plant. Even we visited to the Trombe here, nuclear system. There they are using the CO2 based natural circulation system.
Okay.
So that we can have the more efficiency also. Okay. Means
Okay, sir.
Yeah, this is a very good topic. In worldwide, very few researchers they are working on this. Okay, if you see the scan, one lab is there. I forgot the name. Okay, so few groups are working. Even in that, one of our group from the IIT Patna and the NIT Surat were working, and along with the IIT Kharagpur, we were working on that.
Okay, sir. Thank you.
Okay, sir. Thank you. I will share your details with the participants. So in future, if they want to interact with you, they will having all the details. So with the permission of organizing team, I would like to say thanks to you. First of all, actually your schedule is today at 7:30, but I think because of our first speaker, Dr. Shinde, was stuck in the traffic. So because of that, you are ready to take the session in the 6 o'clock. So that's why it's a thank you from our organizing team. Okay. And thank you for your nice delivering the session. So in future also, we will try to contact with our participants, so they will having the advantage of this particular topic. Thank you, sir.
Thank you very much, sir, giving me the opportunity to express my views regarding this CO2-based system to all the participants. Definitely, if the participants, if they have any queries, and they can reach to us. Okay, so we'll having all the research, everything together. Thank you, sir.
Thank you, sir. Now, dear participants, we are moving ahead for the next session. So the next session, we are having the expert, Dr. Balasaheb Shinde, sir. So, sir is a divisional manager R&D Force Motor in Pune. So, Dr. Balasaheb Shinde is a distinguished expert in the automotive engineering, specializing in the hydrogen power internal combustion engine. He earned his PhD from the Vellore Institute of Technology, Chennai. His with the research focus on the hydrogen ICE technology, and completed his master degree in the automotive engineering from the Pune University. So with over 33 years of extensive experience in the automotive research and development, Dr. Shinde was contributed significantly to the design and develop of both the conventional and the alternative fuel engines and vehicles. His work spanned single-cylinder to multi-cylinder engine for the heavy-duty vehicles and the two-wheelers. He has collaborated with the leading national and international equipment manufacturing, including the Force Motor, PGO, then Bajaj Auto, contributing to the multiple new product development initiative. Dr. Shinde has been instrumental in the several pioneering the achievement, including the development of the India's first MPFI CNG engine for the light commercial vehicle and heavy commercial vehicle application, and the nation's first stroke hydrogen CNG three-wheeler vehicle. His expertise extend to developing engines and the powertrain compliant with the BS1 to BS6 emission norms, as well as contributing to the formulation of auto fuel policy AFP 2025 for the three-wheelers. Prolific research, Dr. Shinde has published 15 plus technical papers in the reputed national and international journals and conference. He also served as a technical paper reviewer for the various journals, including SAE journals also. He has successfully guided one PhD scholar and more than 10 postgraduate students. Dr. Shinde is frequently invited as a guest of honor at the national international conference in India, and has delivered the numerous lecture and the keynote talk on the hydrogen as the fuel and the future at the various universities and the defense establishment across the country, contributing significantly to the nationwide faculty development activities. So such a great personality we have with us for this today's expert session. So with this, I am going to hand over the session to Dr. Balasaheb Shinde, sir. Sir, now the time is yours. You are having the time up to the 9 p.m. Thank you, sir.
Okay. Good morning. Good morning, all distinguished professors. I'm from the industry. Am I audible?
Yes, sir, you are audible.
Yes. And sorry, I stuck up in the traffic, so I could not continue. But thank you. Earlier,
Yes, sir.
presenter has utilized that time actually. I will not take much more time on generally my presentation. My presentation, I keep it in the more interactive and theoretical.
Yes, sir.
So there are not much slides, but I will keep more time on interactive session. It will be very good. Because hydrogen is a new subject, and unless you ask or interact with with any subject, let it be how to play cricket to asking about the how any technology works. So quickly, I will summarize what is the hydrogen and what is going to happen, what is happening in the globally, what is happening in India. Very short, but nowadays you can you can find maximum or the highest subject spoken subject nowadays is hydrogen, and that too a green hydrogen, not only India and in the global market. So I will start my presentation. Thank you, sir, for your nice introduction. Yeah, today's subject is yeah, new hydrogen economy hype to reality. Everybody is till yesterday we're talking about the hydrogen is hype and whether it will work or it doesn't work, or it is only the competition. That multiple questions were raised. Now we'll next session we'll talk about it. To start with, we will go through some hydrogen properties, then hydrogen comparison with the internal combustion engine vehicle and the fuel cell as a competitor, or the supportive technology we can say, then comparison of internal combustion engine, and then fuel cell, battery electric review, then hydrogen in the automotive industry, hydrogen in other critical sectors, then India and the global hydrogen, what is the present status, conclusion, and we move forward. हे काय होत नाही. काहीतरी झालं. हे करायचं होतं मला. Yeah. So, considering the fuel properties, hydrogen, if we compare, am I audible, sir? Hello.
Yes,
Hello.
sir, you are audible.
Yeah. So we'll just compare with the gasoline, diesel, methane, and that is CH4 and hydrogen. Considering the density in the liquid state, that hydrogen is 70.8 kg per meter cube, as against diesel 820 and 845 kg per meter cube. At when you talk about the liquid state of hydrogen, it is at minus 253 degrees centigrade. Density compared with the methane is 0.176 kg per meter cube of methane, against the hydrogen is 0.09. So it indicates it is a lighter gas. Then molar mass is a 2.01 of hydrogen, against diesel is 190. Then calorific value in the different conditions. Then hydrogen 3.19 megajoule per meter cube, against the methane 3.4 and gasoline 3.76. Then mixture calorific value, the internal mixture formation megajoule per meter cube, as gasoline 3.83, against the hydrogen is 4.52. And calorific value, important properties of the fuel. The megajoule per kg basis, the gasoline is 41.5. Methane is close to 50 and hydrogen is 120. So it indicates hydrogen has highest calorific value. Then heating of combustions. When you use the fuel in the combustion, okay, per kg of heat is generated. So on basis of megajoule per kg of air, the gasoline is 2.83 against the hydrogen is 3.37. Then volumetric basis, lower heating value at normal temperature and pressure, kilojoule per meter cube. So the 10,046 as a hydrogen against 1,95,800 as a gasoline. So volumetric density is very low. The CO2 formation is definitely, though no carbon particles are available or molecules are available. So no CO2 emissions. Then gasoline and methane, some carbon atoms are there. So it forms the CO2. Then OB index, important properties for the use of any fuel. The megajoule per Newton meter cube. So it is very close to 40.65 to 48.23 against methane, which is a gaseous form. So this property is being used for the gaseous fuel applications. So 47.91 again to 53.25 for the methanes. And why it is depend? It depends on the methane percentage in the that's CH4 percentage in the methane gas. Then stoichiometric air fuel ratio, gasoline is 14.7 against the hydrogen 30.4. It indicates yes, it requires the more air. Then methane is 17.2. Ignition limits or the lambda, or the wide range of the ignition limit. On basis of volumetric percentage, hydrogen is 4 to 7%. A minimum lean to reach, we can make use of these properties of the fuel. Then gasoline is 1 to 7.6% of the volume. So if we talk about in terms of the lambda range, how much is the excess air ratio? The gasoline is 1.4 to 0.4 against the methane is 2 to 0.6. And as versa, with hydrogen as a 10 to 0.13. Means we can run the engine up to 10 lambda. That is what I did in my research, PhD research. I practically run the engine at 10 lambda. Or the equivalence lambda conditions. Self-ignition temperature of the hydrogen is 585 U, methane 595 U, diesel 250 degrees centigrade. So hydrogen is the safest fuel. Minimum ignition energy, millijoule per millijoule. The gasoline requires 0.24 against the hydrogen 0.07. So it needs very less energy to burn the fuel. And if you want to use this fuel for the different applications, consider the gasoline engine is there, and we want to transform this engine to a port feed injection, cryogenic port injection, and hydrogen direct injections. Then the mixture temperature based on this increase. Then the mixture calorific value is depend on the fuel properties. Then it will be around, if you consider the gasoline as a 3.59. Then if you go with the port fuel injection, it displaces the air. So mixer calorific value reduces. But if you go to the cryogenic port injection as well as direct injection, it increases. The specific power means how much is the power we get. If you consider the gasoline as a 100%, then if you use a port fuel injection hydrogen, it is the 83%, 17% drop. Then the cryogenic port injection, 15% improvement, and the direct injection, you will find the 17% improvement over the base gasoline engine. Then with the hydrogen, if you start using this hydrogen, the multiple applications, that IC engine is one of them. So it will be increase the renewable engine jobs will be increased by 16.2 millions, and other benefits also people will get out of that. An importance of hydrogen ecosystem in India, that hydrogen is emerging as a critical element in the transition towards the sustainable future. India's green hydrogen sector has significant growth potential with the projected CAGR about 20% between 25 to 30, driven by the robust policy, that is the green hydrogen, National Green Hydrogen Mission. When you start using this engine for the different applications, and if you compare this range of this fuel, or consider the 40-ton truck And if it is cost of just a diesel truck is 152,000 euros, then the battery is 354 euros. Against the fuel cell is 486, and hydrogen internal combustion engine has a 250. The average large buses, so diesel cost is 250,000 euros. Against the hydrogen is 700. So in all case, the cost of electric vehicle as well as hydrogen is more than the present conventional fuel diesel. Hybrid powertrain, how it works. Hydrogen, there is a hydrogen tank. It could be a hydrogen fuel cell, then battery, then electric machine which converts this electricity generates, and it will fit to the wheels. So this is general of the fuel cell. And hydrogen IC engine also works on the same structure. Instead of fuel cell, it is having the internal combustion engine. Then power is generated and it is fed to the wheel. Average powertrain efficiency of internal combustion engine with the hydrogen fuel cell vehicle. There are different cycles how to make use of this different testing purpose. So maximum power, if you consider efficiency wise, efficiency WLTP, these are the different cycles. So it is around 25%, and hydrogen fuel cell efficiency is around 45%. And so in all case, hydrogen internal combustion engine vehicle has a lower efficiency than the hydrogen fuel cell vehicles. Hydrogen ecosystem, we start with where hydrogen is produced, then how it is stored, how it is transported, and what are the sources of the hydrogen economy, and where it is to be used. Name it wherever you are using the existing diesel, petrol, or any source of energy. There, hydrogen can be used. Hydrogen is a lighter gas. So we have to use there are two ways to either use it to compress to a high pressure, or compress or make the hydrogen in the cryogenic form. It means cool down the gas to a lower temperature or the subcritical temperatures and use it for different applications. So for using that, different types of tanks are being developed: type 1, type 2, type 3, and type 4 tanks. At present, type 4 cylinders are being used for hydrogen applications. Then volume density, I would say how much gas is filled or with the help of this per liter kg. So type 4 cylinders are 38 to 40 grams per liter. And useful life of all these cylinders, type 1 to type 4, these types are basically on what is the material of the tank and how it is built and what is the procedure they have been used. So type 1 is a metallic tank against the type 4, which is the latest technology. The plastic liner is lapped with the carbon fiber or the grass fiber reinforced epoxy resin. So it is a lighter cylinders are being made. So due to this, but the cost of the type 4 cylinders are high because of carbon fiber and plastic element. But those are being used in the globally. Type 4 cylinders are being used. Okay. Sorry. There is one parameter when you work on any fuel for the different applications. There, the flow rate is directly proportional to the square root of pressure and density. For same hole size and pressure, hydrogen volume rate is 2.8 times of the methane. For hydrogen compared to the methane, like for the like inventories will depressurize in a shorter time. Potentially, the bigger flame is split out and shorter duration of the flames. So that is what how the flame speed, burning velocity with the different fuels. Water and the energy requirement for hydrogen production. How there are different methods to produce the hydrogen. I will clear, but main source is water. So water electrolysis, hydrogen is split in the hydrogen H2 and O2. So how much is the hydrogen or the water required to produce the 1 kg of hydrogen? So 9 kg of water is required to produce the 1 kg of hydrogen. Then ultra pure water is 2.2 meter cube per hour to for 1 megawatt electrolysis. Then how much is the water for 1 meter cube of ultra pure? So these are the different mathematical calculations. Those are available. Estimated variation in the hydrogen demand. So this is the big questions. Everybody in the globally, these are all data. But my personal gut feeling is yes, there will be the definitely more percentage of the hydrogen used in the by 2050. Global experts are talking about the 10% of the global fuel, but I certainly believe you are confident that it will be around more than 25% of the global energy used as a hydrogen as a fuel. And name it where the hydrogen energy or the hydrogen will be used for methanol as a different application. Hydrogen can be combined with the CO2 and different fuels can be produced. So hydrogen has use in the different sectors as a residential heating applications, aviation. Then the biggest is the steel making, then ammonia for making, then heavy duty vehicles as it is you can use it, passenger vehicles, shipping is a big for the transport industries, oil refineries, hydrogen is being used, and light commercial vehicle for transport applications. So these are the different multiple application, residential, transport, and to the industry. So multiple applications hydrogen can meet, and it will lead to a 25%. It is my personal opinion. Low hydrogen, carbon hydrogen production. So hydrogen is produced by natural gas, steam refining process, isothermal reactors, reactor cracking, or the concentrated solar, then electricity, solar waste, biomass, or the byproducts. So all these products, wherever the carbon and hydrogen are there, it can be split and it can be used. Final product is you take any fuel, any gas. If the hydrogen is there, there are different methods to separate the hydrogen from the carbon, and these are the what methods we have now discussed. So hydrogen can be separated from the number of sources, and it can be used for different applications. Specification of off-types of buses considered in this structure. So just to know that what is the application of automotive industry. So solar bus, clean fuel energy enterprises, then the diesel bus or the Hino bus we have just compared, then the electric bus, then hydrogen bus of Mercedes. These are the some research paper data. Then the what models it is, then what is the price and how much is the capacity. All these vehicles are passenger vehicles are 20 passengers to 45 passengers to 31 passengers and up to 58 passengers. Cost of the hydrogen vehicles is more than whatever is the other competitors. Then cost benefit to this diesel powered vehicle, then electric vehicle and hydrogen powered buses. The biggest advantages is, I would say, the emissions norms. All these are the figures and techno-commercial figures. But important out of this, when you go with the electrical vehicle, there is no CO2 emissions, and hydrogen vehicles, there is also no CO2 emissions. So those are the complementary technologies for CO2 reductions. And this is the hydrogen supply chain, where it is source of hydrogen. You can, as I earlier said, it could be anything. It could be coal, biomass, natural gas, okay, or hydro, or solar, PVT, or wind. All these energies we can be the energy sources can be used for hydrogen production. And methods could be gasification, steam reforming, or the electrolysis of the water, then steam reforming or the electrolysis. So all these based on the whether carbon is captured or not. So that is the different we say hydrogen production methods, and then hydrogen is stored in the different forms. Hydrogen is naturally in the compressed form, or the metal hydrides or liquids, or cryogenic compressed hydrogen or the compressed hydrogen, different methods. Then distribution could be gas, pipeline, container, or liquid container, or CH2 the trailers. So different methods are there. Then refilling, when it comes to some reuse station, then it has to be nitrogen from deblending, then it could be gaseous. Again, it can be compressed, or hydrogen can be released by the meter hydride storage technology, or it could be a liquid, and it can be again used for the different, it convert to a gaseous form. Then it will go to a dispenser, either it will be a liquid dispenser or the gas dispenser. And if you go to gas dispenser, it will follow the same route as CNG, which is presently being used in India as a 200 bar pressure, or LNG as a liquefied petroleum, liquefied natural gas. Hydrogen storage could be compress, liquid, or cryo compress. Then what is the density and pressures and all these details are there. But hydrogen can be stored in the different medias. That is what we want to show it here. For aviation, just like on-road applications, automotive or other applications, the hydrogen can be used for aviation application. There are different industries working hydrogen as automotive, hydrogen as a fuel for aviations. So it can be used for fuel cell applications, or it could be a liquid hydrogen, or the on-site hydrogen generation. Everybody might have understood or learned or informed by the Prime Minister of India. So we are also developing the hydrogen train in India. History of hydrogen. Hydrogen is not today's fuel. It has started IC engine fuel as 1807 by the researcher D. Rivas. First, he started working on hydrogen for small application, and then it started. There were 3-4, I would say, cyclic development took place globally for hydrogen as such. Many times it has stopped as a due to geographic conditions or availability of fuels, or availability of competition of the other fuels and availability, and multiple questions were being raised for 3-4 times. Hydrogen wave came and it has vanished. But this time, believe on me, this time hydrogen will take globally. That is the only solution people, everybody has understood. And not a single nation has left out working on hydrogen. And there are some companies where they started, they were working since 1972 to 2000. Take example of BMW. First, they were being used for the luxury applications, small car applications, and then other applications are JCB, Isuzu, and then Pakar also. Pakar is also a company who has working on the hydrogen as a fuel for IC engine specifically. Then MAN has also done some research for the trucks and bus applications. There are other companies also in Japan. They have worked on hydrogen IC engines. The QA is one of the company. They are working, German company. They are working on hydrogen IC engine since 20 years, and they have developed the different product. They are working on 13-liter direct injections and got the efficiency at 41 point brake thermal efficiency. Cummins is also working on 6.7-liter H2IC concept car. Then Toyota, then Cummins bigger engine applications, as well as Borg-Warner hydrogen direct. So hydrogen has a different application: portfolio injection, direct injection, or high pressure direct injection. There are a few companies working on Westport, like a company, they are working hydrogen. high pressure direct injection. So Daimler is also working on hydrogen PFI technology. In short, every other global players are working on hydrogen IC engines. Global development, European, the Fit for 55 means European Green Deal fashion exactly allows the H2IC engine. Earlier, they wanted to ban, but after studying the different applications of the hydrogen and use of hydrogen as a fuel, and they again implemented or the legislation allowed to use engine with the hydrogen internal combustion for automotive applications. Then United States has a carb heavy duty emission of 100% zero emission vehicle by 2045. India is also same strategy 2035 national green hydrogen strategy focus on production and industrialization. Then foresee H2IC fuels and H2D1 liquid fuel for transport, hydrogen and S3 IC engine for different applications. We are not left out to the automotive, but for the marine application also. Japan, Korea, and China, including Australia, everybody has started working on the hydrogen. The hydrogen could be a different colors, green, blue, or brown, or different source of hydrogen. But application is important of that. Yes, and today's India's strategy for the hydrogen production. The Andhra Pradesh has 3.5 to 4 lakhs crores investment for a different. Maharashtra has a 2.763 lakhs crores. These are the investment for hydrogen production and application of the different sectors by the different companies. Then Odisha 2.2 to 1.4 lakhs crores of investment. Karnataka is the again highest one. 2.9 lakhs crores of the investment for the different players for different applications are there. So we as India is not behind the globe. We are also we are the fourth largest economy. So we are taking active role in the development of the hydrogen technology. And that what I said is we are also last year Reliance has developed the trucks and bus along with the Ashok Leyland. They are flying on the road. The testing is going on. There are other players also there who they have developed their vehicles on hydrogen fuel cell. And as I mentioned earlier, there are other applications of this hydrogen. So hydrogen train is developed by Government of India. It will be rolled out for the public use very soon. So if you can fast solution of decarbonization of the transport sector is hydrogen, both H2IC and fuel cell are complementary to each other. Meaning is both technology is as the hydrogen as a fuel for both applications, IC engine as well as the fuel cell application. It is most suitable for LCV, SCV, marine, rail, and different applications. For two-wheeler and three-wheeler with the low energy is required. Battery electric technology is suitable. That is what we have seen. Sale of the two-wheeler and three-wheeler. Three-wheeler is the highest sale vehicle in the world. The electrical vehicle. If you look at the last year or this year electrical vehicle application data, then that is why we'll continue to work towards the hydrogen economy to meet the global net zero emissions. And hydrogen is, again, I'm telling what my intention was to show the presentation quick so that we can take more time for the discussion. So it is certainly hydrogen is not hype. Now it has came to a reality, not only in India, but in the global sectors. Thank you. Yes, sir.
Hello.
Yeah.
Yes, sir. Just a minute.
Mhm.
Thank you, sir, for your
Yes, sir.
nice presentation on hydrogen fuel. So I think you've covered all the topic, and it's really interesting because you mentioned all the scenarios of hydrogen. Today's hot topic of hydrogen production, its application, and its storage. So you cover all the things with the worldwide scenario. So I request to our participants, please, you are having any queries, you can interact with our today's speaker, Dr. Balasaheb Shinde. So you will be unmute yourself and you can directly talk with the sir. Participants, please unmute yourself and you can talk with the sir. Otherwise, you can write in chat box. Okay, sir, I will share your details with the participants. So in future, if they want to collaborative work with you related to the hydrogen fuel, so they will write or they will contact you.
Yeah, I'm open to. I'm working with the global. I'm in contact with the global experts available out in Europe and Asia level.
Yes.
Anybody would like to know more about the hydrogen, would like to work on hydrogen IC engines, I'm open. You can call me at any time.
Yes, sir. Yes, definitely, sir. Sir, I have the question for generating the hydrogen. I think in your slide you said some 7 liter of water is required, like that only. So what about the energy, sir? Any different energy is required to produce the hydrogen, and what is the rate of that?
Energy, for example, if you want to use the electrolysis of water, so 9 liter of 9 kg of water is required to produce the 1 kg of. So energy required is 45 megajoule per kg. So energy required is more compared to other technologies. So this is the green hydrogen. So if you talk about the blue hydrogen, so blue hydrogen is generated out of methane reforming process, steam reforming process. So steam. And if you are not capturing the carbon, so when you split the CH4, the carbon is separated, or the CO2 is generated. If you capture it and store it, so it will be treated as a blue. If you don't use it, capture it, it will be treated as a brown hydrogen. So their energy requirement is less than the electrolysis.
Yes. Okay, sir. Thank you, sir. So one more question is there. Is the pure hydrogen is used as a fuel? If yes, then the coil cell, like that some mention, coil cell emits heat and water byproduct. One of the questions, sir. Is the pure hydrogen? Yes, sir.
Right, sir. In both applications, hydrogen as well as fuel cell. Hydrogen it is the as 100% pure, but impurity maybe could be 97, 98% of the hydrogen is suitable for IC engine applications. But if the same fuel you cannot use for the fuel cell application because it needs ultra pure hydrogen. So 99.9% of the hydrogen. Otherwise, the fuel efficiency of this fuel cell deteriorates. So that is why for getting the 100% the pure hydrogen, it is a costly affair. Then hydrogen with the 97 or 98% of the H2 hydrogen can be used with a lower cost in the hydrogen IC engines. And same like if you use the hydrogen in the IC engine, you will find the water vapor as a when it comes out of the silencer, it will get condensed. So you will find just like CNG or the gasoline vehicle. So early in the morning, it is water drops are coming out of the silencer. Same you will see only the water is coming out of silencer in the hydrogen IC engine, and fuel cell is also same.
Sir, now you are working with the national, international agencies and the peoples who are working on the hydrogen engines. So
Yeah.
now can you say about the how much time is required to see the vehicle on the road that will be run by using the hydrogen? And once it is run on the road, then what type of challenges we can face? Like today's we are having the EV vehicle, but we are not having the sufficient charging station and all these things. Even if the CNG, we are not having the sufficient CNG station in the different areas. If you accept the metro station and metro cities like that only. So what challenges we will face in the future if the hydrogen vehicle comes on road?
Important is, I will not talk about electrical because electrical has its own geographical issues. What is the property and that material availability, and where is the material, who is making hydrogen, who is making the electricity, how to store. Another thing, where we'll get the electricity. For a country like India, yes, solar can be the one of the source. But if you take example of the European countries, they don't have the source of natural source of sun, so they have to buy the energy or electricity from the other countries actually. So that will not be the case with the hydrogen. Hydrogen is such fuels, there is no geographical constraint. Anybody can use make use of any electricity available. Means PV cells can be put up, it can be generated, stored, and it can be used for any application, domestic to national applications. And so we don't have to import the hydrogen. Rather, we as India as a biggest plan to export the hydrogen for different applications. That is what we might have seen, that the green hydrogen, green ammonia, people are talking in the newspaper. So that is, we'll produce the hydrogen or the green hydrogen and we'll export it to. And just like electricity, this won't be a problem. Please understand. So why we were continuing still CNG as a problem? If you look at the early in the morning, if you look at the any newspaper, you will find that Delhi is the most polluted city. What is wrong with Delhi actually? If the government has started 10 years before, also the electrical vehicles, how many electrical vehicles are there? I am not the right person. I am speaking on the public. It is not right to speak against electrical. But as a technocrat, I know the problem. I understand the technology. So I will skip to speaking on electricity. But hydrogen, you can make it anywhere. Means one city or one village can make a hydrogen by its own, by different means. Means they can use the biomethane. You might have seen the biomethanes can be produced in anywhere. Then you can convert the methane to hydrogen. Means any specific village also can produce, will be a self-sufficient for the hydrogen. And hydrogen can be stored in different applications, different types of hydrogen storage. It can be used for two-wheeler application, trucks, buses, or we are also working on some of the project for domestic applications.
Okay.
Important is we want to use the energy where the carbon or the CO2 emission will not be generated. That is the main attempts. And we don't have to import the hydrogen, whatever the water available or the methane available. Why to pursue for the further fuels which is having the carbon? So we should research, or rather research has been completed. And again, to your first question is globally 26, okay, 2050 is now ending, 26, 27. Starting from 27 to 28, you will find the vehicles flying on the road.
But we need to set up the charging station for the hydrogen, like a petrol pump or EV charging station is available on highway. So such type of station we require.
Yes, those stations, government of National Green Hydrogen Missions, that government has a budget of 19,000 crores. It has 2023, they have given the declared that scheme, National Green Hydrogen Schemes. Under that scheme, government has put up some hydrogen fueling chain pump. Means that I will just explain what is the green hydrogen plant. That is for everything. That is, if you want to produce the hydrogen, that is why some of the hydrogen production plants are being set up in India. That is what I have shown. Then the hydrogen, for the hydrogen production, we need to produce the electrolyzers. So government is giving the PLI scheme for the electrolyzers. Some research projects are being developed. So somebody will put up electrolyzers. Electrolyzers will be used for the generation of the electricity, and that can be used, or it can be used for the hydrogen generation. So it can be stored for different applications.
Yes, sir. Yes, sir. Sir, we are having one more question in chat box. The hydrogen has been used as a rocket fuel. Would you consider as a clean fuel than the CNG?
Yeah, naturally, hydrogen. Okay, the question asked is very, very important.
Yes, yes.
When it is for rocket or any internal combustion application point of view, when you use the hydrogen in internal combustion engine, so when it has to be used for the linear combustion, but you will find some percentage of the NOx generation, oxides of nitrogen generation, as a product of heat. But compared with the hydrogen generating the NOx and the hydrogen generate and CH4 methane being used in the IC engine, so NOx generation will be the more in case of CNG vehicle than the hydrogen. So hydrogen NOx will be generated, but again here the carbon molecules are not in the hydrogen, so CO2 generation will be definitely zero. And here in the CH4 or the methane, the CH4 that CO2 generation is there. So main attempt of the global, or we as a technocrat should be think of use any fuel which will not generate the CO2. Forget about, there are other components, CO2, NOx, that can be treated with some means. Make sure that we'll use the fuel without carbon. That is, the hydrogen is the one fuel at present.
Hello, sir. It's Dr. Santosh here.
Yeah.
Sir, if I am using hydrogen to run an engine, it produces also nitric oxide. It is also a toxic.
Yes.
Then how to minimize that nitric oxide?
Sir, if you look at this hydrogen optimization strategy, we don't run the hydrogen in stoichiometric conditions. That is what we have seen. The lean limit of hydrogen is higher. We have to run for 2 to 2.5 excess air ratio. There the NOx emission reduces to a very little level. And even if it is some NOx is coming out of engine, and there are different technologies being utilized. I'm not saying research will. They are experimented and they are in the productions. That ACR is one of the technology where the nitrogen is converted and to a minimum acceptable levels.
Okay. Thank you, sir.
Okay.
Yes, dear participants, if you have any queries, you can interact with sir. Otherwise, we will conclude the session. Sir, I will share your details with the participants, so they will interact with you in the future. Okay. So thank you for accepting our invitation. So on behalf of organizing committee, I'm thankful to you for accepting our invitations and nicely delivered the session on the today's hot topic, that is the hydrogen and its use in the engine and the automobiles. So thank you once again, sir.
Thank you all. Thank you, sir.
Dear participants, our today's both the sessions are over nicely. So thank you for your patience. So I will share the both link in WhatsApp group after 5 minutes. So now you can leave the meeting. I will share the link for the feedback in the WhatsApp group.